Okay, so here I have an example of a typical binary star system where you're given two different masses, and the two masses are a different distance away from the center of mass of the system. All right, so if you want to take a second, pause the video, look at the diagram on the right. That will help you understand this particular problem. The statement says there are two stars orbiting around a common center of mass, and then it gives us that R2, the distance from M2 to the center of mass of the system, is 4 times R1. Okay, and it asks us to find the orbital period of the binary system. So to go ahead and do that, we first set up a physics statement that is the centripetal force is equal to the gravitational force of attraction. Here, I've chosen to select M2 as my perspective. So M2 being the yellow dot or orange dot here on the left side of the diagram. And then from there, I can just go ahead and apply it. F of C is mv squared over r. Here is M2, V is V2. So be consistent with your perspective. It's M2, so make sure you use V2. And then R2 is in the bottom here. I went ahead and color coded red here because R2 in the given statement is 4 times R1. And then f of g by definition is g, the gravitational universal constant, times m1 times m2 divided by the distance between the two masses. So you notice here in the bottom, or in the denominator, I have r1 plus r2 in parentheses because if you look at the diagram, the distance between m2 and m1 is r1. If you watch my cursor, if I start from m2 all the way to the center of mass, that's the distance of r2. But I need to take it all the way to the next object, which is m1, and that is an additional distance of r1. So the whole entire distance between the two masses in this case is r1 plus r2, according to this particular diagram. All right, so from here, we can just go ahead and cancel out m2. It appears on both sides. And then we just go ahead and combine like terms and then do a little substitution here. All right, so r2 can be replaced with 4r1 because that's given in the statement. And then down here, instead of red on the right side, R2, I went ahead and substitute that in for 4R1. And then you notice here, now we have like terms in the denominator on the right side. R1 plus 4R1 will give us a sum of 5R1, which I've gone ahead and reduced for you here. All right. And then from here, we just go ahead and isolate for V2 squared by simply multiplying both sides by 4R1, which is what I have in the next line here. And then I went ahead and distribute the square in the denominator. So 5 squared will give us 25. And then R1 squared is just R1 squared. And then from here, we can clean up a little bit. You notice in the numerator, you have R1 by itself. In the denominator, you have R1 squared. So you can go ahead and cancel one of the R1s in the denominator out with the R1 in the numerator. So I've go ahead and cancel R1 completely there on the numerator, and then just cancel the square symbol there for R1 squared. And then that's going to give us, a function to play with, okay? And then next, we have to substitute V in terms of 2 pi r divided by capital T being the period. So we want to do that because this particular problem asks us to find the orbital period. Okay, so we got to introduce T in this particular next statement. And so V by definition is the distance divided by time. The distance in this case being the circumference of the circle, which is 2 pi r. But you notice here, I didn't just write r, I wrote r2 because we're looking at m2. So the radius, quote unquote, relative to the center of mass that m2 traces out is labeled as r2. And then the time is capital T for the word period. And then I just carried the square symbol down here on the left side. All right. So what I did in the next step here is just I flip-flop everything upside down. We're asked to solve for T. And because T is in the denominator, I went ahead and square everything inside the parentheses, and then I flipped it upside down so that I can get T in the numerator. But what you do on one side, you have to do to the other side. So I went ahead and flipped the right side of the function as well. So the 25R1 in the denominator is now in the numerator. The GM14 was in the numerator. It is now in the denominator. So here in this line, I have T squared in the numerator, which allows me to go ahead and isolate for T or an expression for T, okay? All right, to get T by itself, let's go ahead and move all this junk in the denominator, the 4 pi squared R2 squared in the numerator by multiplying both sides by that term. So if you do that, you get this particular set. So it looks like a lot of work here, but I just kind of wrote everything out for you. So it would be 25R1, which is already in the numerator, multiply both sides by 4 pi square r2 square, which is what I have here. But you notice here I have r2 in red. That's because in front of the parentheses, we have r1. Inside the parentheses, we have r2. And we can go ahead and substitute that particular r2 for, again, for r1 because it was given to us. And we can just clean things up a little bit. And you notice here in the first radical, I have a 4 in the numerator. I also have a 4 in the denominator, so I went ahead and canceled that out. So in the second equal sign here, you don't see that 4 at all. So I went ahead and canceled out 4 and 4 just to clean up a little bit. And then here, good habits, make sure you use parentheses when you substitute. So notice here I put R2 as 4R1, but I put that in parentheses because you need to distribute this exponent to the 4, which will make it a 16. And you need to distribute the square to the R1, which will make it R1 square. But then you also have an R1 here where my cursor is. So if you take R1, multiply R1 square, you'll get R1 cube. And the denominator stays the same. So if you do 25 times pi square, which is just some number, times 4, and then take the square root of that, you should get a value of 62.8, which can be pulled outside of the radical. And what remains in the radical is 1r cubed over gm1, and that matches with choice B. Okay, I hope that helps. Stay nerdy and don't be whack.